Hi, welcome again to this second video of internet is not working situations that I'm currently facing. Still sorry about that. Today was supposed to be a case study, so I've changed it a little bit. So it's less of a case study, is more of an example. And on Friday, when we'll be back to live lectures, it will be more of a case study, and we're gonna like do things together and experiment things on the board. But well, situation being what it is, we're gonna go for this pseudo case study related to comparing things in the context of the course. So we're going to look at what does it mean to compare things, because that's something that you will often have to do in software development. And we'll see, like, first, this can be done in an embedded way. Secondly, we'll see how to externalize this and how to kind of like decide when it needs to be embedded and when it needs to be externalized. And finally, the last part of the lecture will be more about how to compose services when you have a class that is exposing and offering multiple services, realizing multiple interfaces. How can you structure this so that it becomes sustainable from a development point of view? So first, the notion of comparison, just a quick reminder of what it is, and this idea of embedding it, like the idea of realizing the interface, and that's what's called in Java the able approach. In Java, and that's the case in lots of mature object-oriented languages, there's a lot of services that are common, like it's off the shelf. You often need to clone objects. You've seen the problem of copy in Sam's lecture last Friday, and that is very ready to which level is your clone, how deep should you go. You have the notion of serialization when you have to exchange objects over the network or to save those objects on the disk. How can you do that? Notion of comparison. In the previous lecture, we've seen this notion of iteration, like how can I go through a collection of elements. Things can be runnable, that can be executable, they can be callable like a method. It's an object, but that realizes a function. I'm going to use this object as a function, can be observable, can be closable for streams. Like there's a lot of those services that you can define as abstraction. Remember from the last lectures, this notion of drawing things from a source. This can be done whatever the source and whatever the drawing is, okay? So whatever the concrete drawing is. So that is the very same idea. By having this like definition of abstraction as functional service, functional behavior, like what does it mean to iterate, what does it mean to compare, what does it mean to run, to serialize, to clone, then you can build on top of this cool features that just doesn't care about what's concretely executed at the bottom at runtime. So the contract, the whole idea is really like, if you define a class and it realizes the X-able interface, it means that it provides X as a service. There's a slightly different here for serialization, which is kind of an alien and is not really following this, because to be serializable in Java, you don't have to implement anything. You just implement the class and there's no code from you. It's like automatically provided by the language, but that's an exception to the rule. So you want to be clonable? Well, implement clonable. Tell me how to clone. That's fine. You want to be iterable? Implement iterable. Tell me how to iterate, and that's fine. You want to be comparable? Well, implements comparable. Implements comparable. Tell me how to do that. Implement the body of the method, and everything will be fine. And by doing this, by really focusing on those layers of abstractions, that's how you define reusable software and extensible software, and that's one of the main differences between development and programming. If you're programming, you just don't care about the maintenance, you don't care about the lifetime of your system. You just wrote it, it works, that's done once and for all. If you're thinking in terms of engineering of the product, well, you don't want all your code to be tied to one single implementation at one moment in time. You've realized during your assignment that, well, you're taking a decision, they're not the right one, so you're going to fix it. So the more flexibility you give to your code, the easier your life will be, and the easier the life of your teammates and the other engineers that are going to work on the program will actually be simpler if it's kind of flexible. So having those interfaces, that's a good way to be able to provide this level of flexibility and also this level of like high level contract. Whatever the stuff is, if I can compare it, I can assume that it was implemented the right way, so I can express my functionality in terms of comparison, whatever the concrete type is, which is really super important. There's a downside here, which is important, is that if you have too many interfaces, like if you put too many layers of abstraction, then it becomes a nightmare because you don't know what to use, and it's super painful and super verbose and really, really complicated and heavy weighted. And remember, we are here to do the right thing. So build the right product, build it the right way. So if you have too many interfaces, if you introduce too many abstraction layers, too many interfaces, too many relationship between your models and your code, those will be terrible models and that will be terrible code. So it's always about trade-off. And that's why you should not be into a mode which is asking the prof, the instructor, the TA, whoever, like, should I do this? Am I allowed to do that? Or those kind of things. You're allowed to do whatever you want, as long as you can explain why you think it's good and why you think it adds value or to the functional service or to the technical excellence. Why doing this kind of complex inheritance makes sense. Like, you have all those interfaces. Does it make sense? If it makes sense, yeah, sure, go ahead, do it. If it doesn't make sense, nah, that is accidental complexity. That is technical debt. You should not do that. Okay. So it's related to what we were saying last time. Be in control, know what you're doing, know why you're doing it. And then that gives you like global control of what you're developing, because you're not programming anymore, you're developing. So if we think in terms of abstraction, if I want to sort something, like whatever this thing is, a collection, an array, a list, whatever is ordered, not a set, of course, because a set is not ordered, but let's say an array or list. Well, to be able to sort, like find the right way sorting your grades, for example, at the end of the semester, ranking your GPA, whatever, ranking the result of a competition, like whatever that requires, like there's a first element, second element, third element. You'll see in your data structure and algorithm course a lot of sorting algorithm. It's kind of like essential in software engineering and in programming in computer science. So to be able to sort, I need to know which element is smaller and which element is bigger. Okay, so I need to be able to compare. I need to know that E1 is smaller than E2, and so put E1 before E2 if I'm sorting and increasing order. Okay, to do that, well, there's this notion of comparison in Java, which is the interface comparable. And if I'm implementing comparable on my element, then any collection of this element can be sorted because the sort is defined over comparable. And this makes the language and the possibility, the expressiveness of the platform infinite, because anyone who comes with any business domain, any business application, anything, any class, just have to implement comparable and then immediately can reuse all the sorting algorithms that are available in Java, just because you provided a comparable service. Because the sorting algorithm were defined using the right abstraction. You just have to insert yourself under this abstraction, and then everything's fine. You can do whatever you want. Okay, and you can reuse all the stuff provided by the language. So that's really important. And that's really like actually putting into motion and putting into practice what we've seen in the last lecture. Last lecture, we're like, okay, this is how you can do it, and this is how to implement it. But this one is really like, this is how it was implemented at scale in something as complex as Java. The sorting algorithm, the sorting method, the sorting library in Java know nothing except the notion of comparable. It's only coupled to the notion of comparable. So from the sorting point of view, we are not a card, we are not a student, we are not a cohort, we are not a class. We're something offering comparable. Whatever you are, if you're providing comparable, I can sort you. Get the point? But there is something important here. If you realize a service, like, it's a contract, so you need to do it the right way. A comparison, that's an order relation. So you will kind of like have to remind your discrete math course for all the details. I'm just giving you back the kind of like what is needed here. An order relation is built on top of three principles. So to be an order relation over a set of instances, of a set of elements, you need to have those three properties to be qualified as an ordered relation. First, you need to be reflexive. You need to be able to compare one element with itself. Secondly, you need to be transitive, okay? If E1 is smaller than E2 and E2 is smaller than E3, then E1 needs to be smaller than E3. If not, that would be super weird. So reflexivity plus transitivity that give you the notion of pre-order. You're not an order yet, but you're into the direction of being an order. And if you add the anti-symmetry property, then, which means that if E1 is smaller than E2 and E2 is smaller than E1, then E1 is E2, then you have an order. Because on top of the three pillars, then you can define an order relation, okay? We're programming language, so it's slightly more annoying than the purity of mathematics. So we also have to be able to compare to null, because in Java, there's this weird object, which is nothing, that might happen. Okay, so that's a famous, dreadful null pointer exception. So this can happen. So we need to take this into account. We don't want to crash just because at some point we don't have an object, but we have null. Meaning that we're like dealing with a partial order. That's annoying from a math point of view, but we can deal with it. And if we have those comparison, well, we can define actually equivalence classes. Okay, two elements are equivalent if when we compare them, we answer 0. Means, okay, I can't distinguish them according to this equivalence relationship. If I reply -1, it means that, or any negative number, it means that E1 is smaller than E2. If I reply a positive number, it means that E1 is greater than E2. But if I answer 0, it means they're indistinguishable. Okay, I can't do, they're equivalent. So back in Skodentoten, if you want to compare two cards, remember a card in Skodentoten, it's a value from 9 to 1 and a color. And the colors are like black, yellow, blue, brown, whatever. The color doesn't matter, okay? It's what's really important, the value. Like 9 is greater than 8, which is greater than 7. But 9 blue and a 9 yellow, well, they're both 9. So being blue or being yellow doesn't change anything in terms of the order relation for the game. So basically, we have an equivalence class here defined over the colors. Like we don't really care about the colors. Any 9 is equivalent to any other 9. To implement this in Java, well, we need to be able to compare colors and values. Colors and values are both enumeration, so they're basically kind of like automatically ordered. Okay, it goes by the way you declare. The first one, the most important, then second, and blah, blah, blah. It's kind of like a syntax hack that will help us here. Other language might require you to define also how to compare values among others, but that's just like, you get the point. It's one of the services provided by the language. Colors, okay, it's enumerated, so it has an order relation. We're just not going to use it because we said that colors are all equivalent. And in our case, if I want to compare a card, well, basically my card implements comparable, so it provides a service of being comparable for card, because it could be comparable for other thing if it was providing other type, for example. And to compare myself, this, with any given card, well, I will basically delegate to the comparison of the value. I don't want to take the decision at my level because this decision can be insanely complicated. In our case, it's not, but you get the point. So my responsibility as a card is to say, oh, you want to compare? I want to be compared with another one. Perfect. I'm composed of a color and a value, which is important is the value. So I'm going to delegate to the value the fact of being compared. It's very important to get there here, this notion of delegation. Being an object-oriented design and an object-oriented programming language is always delegating. I don't want to do something. I know someone able to do something. Let's ask this person to do it. Ask this object to do it, okay? I could, of course, I have written in my compare to method in the card class the comparison of value, but that's basically the responsibility of value because value knows how to compare itself with another value. So I'm not overstepping anything here. I'm just like, oh, being a card, being compared at a card means ignoring the color and being compared at the value. The value knows how to compare itself. I'm delegating to the value. I'm lazy. Actually, I'm not doing something that someone else can do on my behalf. So that's why my actual comparison for a card is simply delegating to the notion of value and say, okay, then take my value and compare it with the other value. And that's implemented quite easily. And because I'm doing that, well, now, as my card is comparable, I can basically say that my card pile is a collection. Okay, I can realize the notion of collection. And so, well, because I'm comparable, then I can sort, and that comes for free. I don't have to do anything to sort my card pile just because I've provided an implementation of comparable, which is pretty cool. Cordell's limitation, okay? There's no such thing as perfection in terms of software design. And the whole stuff is about weighting pros and cons. And that is something which is really, really important in that case. And in your assignments, in your projects, in your like whatever you're going to do, you basically have to weigh the pros and cons and find the less worse situation, because the perfect one doesn't exist. So take a decision, know why you're taking your decision, be in control, know your poison, know that like the limitation of the decision you've taken, and at the next iteration, you'll be able to fix them, or maybe not, because they'll, okay, there's limitation, but there's limitation based on cases that never happen. So maybe it's not such a priority in terms of development to fix these kind of things and to repay my debt on this part. Maybe have more important things. Always a trade-off, always a balance between what to do and how, when to do it and how to do it. So what you can do is try to like go back to this idea of, okay, the card now is comparable, so the card pile can be sorted quite easily, and the card is made of a value and color, and try to think about what would be the problem in terms of evolution, in terms of maintenance, because that works. I mean, we've done it, it's implemented, everything's fine. Check, I can deliver. Now I can sort my card deck, or I can like compare cards together. And then when you kind of like think a little bit about it, then restart the video. So basically, our case study might be a little bit too simple because we have only like one card game where the notion of card and the notion of deck is really like tied to the rule block. There's only one way to compare the cards. So if there's only one way to do things, then finding the right class to hold that responsibility, and who else better than the card knows how to compare itself with another card. Well, that would be weird. So it's kind of like fine to give it to the card. But this is done once and for all, and that's it. So it's a responsibility of the card. The card know how to compare itself with other card. That's it. But if we have several ways of comparing cards, then we might have a problem. Think of a regular card deck, not the Scotland 2001, but the like regular with ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, 2. Okay. That's usually the way the cards are ordered. Pretty cool. There are some games that have extra cards or stuff, but still, that's pretty way, like regular way of ordering things. I don't know if you know the Belote game. That's a game where when you play, you decide which, like you have some bets and you decide which figure, which family, which suit is the trump. And if it's a trump, then the order is jack, 9, ace, king, queen, 10, 8, 7, 6, 5, 4, 3, 2. And if you're playing with a regular suit, then it's ace, 10, king, queen, jack, 9, 8, 7, 6, 5, 4, 3, 2. Okay, so it's kind of like this weird beginning of power between the different cards that change the game dynamic. Okay, which means that if we continue to give to the card the responsibility of being comparable, we can't do that anymore, because the card needs to know if it's a trump or if it's a regular suit. And this is not the responsibility of a card, because, well, a card is a card. So it's just like, it's not possible to influence the behavior of something internal with something external. A card, by realizing comparable, should always use the same comparison and not have inside its very definition, inside its encapsulation, hiding its information, something which is if I'm a trump, if I'm a suit, if I'm in this game, if I'm in that other game. Well, no, you're a card. You just be a card, and that's it. So if we consider several ways of comparing cards, giving the responsibility of being comparable to the card just doesn't work. It's a design flow, because then that will become a bottleneck. That will be like something that would be influenced by external factors, which is something not good. So that's a responsibility problem. And what we've done was okay at some point. Okay, it was the responsibility of the card to compare. Pretty cool, neat, on point, worked. But if we had like a different solution, different situation, a different solution is needed. And in our case, well, if we don't want to break encapsulation and information hiding, like having this pure way of taking care of things like, okay, that's it. I'm just asking the card to compare with others and that's it. I have to find something. And if I can't give that responsibility to the card, well, it looks like the influence comes from the game. Because we're playing Belot that, well, suddenly I have different way of comparing the cards. So maybe giving the responsibility of being comparable, like the comparison mechanism to the card, is a little bit restrictive. So maybe giving it to the game that hold the cards might be the right way. How can I choose between those? Well, Scott and Totem, it's dedicated cards that were defined for that very game. So they will not be used by any game. So there is no variation here. So providing the card giving to the card a way to compare itself with the others makes sense, because there is not like, what if we blah, blah, blah. It's just like, oh, the card deck was designed for that game. So let's do it for that card deck. But if you take regular card that can be used to play any game, even if there are still cards, doesn't make real sense to embed this meaning inside the card, because the cards are generic. They're going to be used in several games. So the point here, the element who hold the responsibility of telling what to do with the card can't be the card anymore, because if not, it will be like way too tight, way too coupled to given semantics. So you have to give it to someone else. So you see, both cases, we're talking about comparing cards, but depending on the situation, I'm going to take a totally different solution, just because the objective in terms of development is totally different. In one case, it's a closed world, one single game, one single card deck, so it makes sense. In the second world, in the second example, it's an open world. We can play any game with that. So that would be wrong to give it to the card. That is related to what I was saying about justifying, defending what you need. If you take the open world situation and apply it to Scott and Totem, then it's just wrong. That's not the right way of handling it. So your justification doesn't hold. Okay. So when you do something, think why. Why are you doing this? What is bringing as a value, as technical excellence value? How are you increasing the technical excellence of your code by doing this? And that is very, very important from software engineering point of view, from development point of view, that you are able to defend, because it's not just about coding, it's just about coding it the right way. And there's no silver bullet right way, which is good for any situation. We've just seen here that same stuff, like comparing two cards, but very different solution in the end, because in one case, I need to be adaptable. In the second case, it's not the case. So this is quite classical. That's why we're reading the comparator example, comparator and comparable. Java also provides a session of comparator, because that's often that things need to be compared differently. If you want to sort students, you can sort by the number of credits they've achieved. You can sort by the GPA. You can sort by the number of semesters they spend at Mac. Like there's a lot of way to do it. So you want to have this defined outside. So there's a notion of comparator. And you can create those comparators that say that, oh, I'm an object, which is compare by value object class, sorry, that implements, that renders the service of being comparator for the type card. And now I'm not comparing myself with another card. I'm comparing two cards, okay, C1, C2. And then, oh, then C1, I will take its value and I will compare it with the value of C2. And you see, we're starting to have some encapsulation issue here, because I need to be able to expose what is needed to support my comparison. For this slide, I've used internal classes, so I have access to basically virtually anything, but that's another kind of like encapsulation issue. It's just like, so it fits in the slide. And you know it's possible. But basically, if now I've taken the notion of comparison and I've take it out of my object, my comparison needs to have access to the content of the object so that it can drive the comparison process. Okay, it's a trade-off. I'm kind of like allowing any kind of comparison as long as I'm exposing some of my internal contents, which we've seen 2 lectures ago, that can be an encapsulation problem. Trade-off. Nothing is better than another one, just something is slightly less worse than another situation. Get the point? Don't look for perfection. Just do things by knowing why you're doing things and why it is the way it is. And that will be way better. So based on this and this comparison, which is a compare by value, I can actually have my sorting in my card file by saying, hey, we're going to sort my cards using this comparator. Okay, so now it's not the card that is providing the responsibility. I need to give to the sort algorithm, hey, use this comparator to be able to do your job. But that works also quite well because the sorting algorithm knows how to use a comparator. So anything that is a comparator can be used to support the implementation of sorting, which is pretty cool. And they're like pretty classical objects. So if you need to invent an on the fly way of comparing objects, you can basically instantiate your objects on the fly. Like this one, it's a new comparator. It's an anonymous object. It doesn't have a class associated to it. It's just like, oh, by the way, I'm just implementing something that gives me the notion of comparator, and I'm giving you the method about how to compare, and that's it. So I'm not creating a new type. I'm just like on the fly instantiating an anonymous comparator. This is Java syntactic sugar. It's just for you to know that this is possible and that you can do it. And that's just like, it's a way to kind of like remove the heavy-weighted approach of Java, which is one class, one file, and that can be kind of a burden. So there's no need to create a dedicated class for something that could be just like, oh, I just need like for 1 second, let's use it, and that's it. And actually, if we just like push it a little bit more on the hack dimension, you have this notion of a lambda function in Java that can be used. And this notion of lambda function is sort of like you have the card, and this is basically the comparison is done by comparing 2 things. So it's a function. And I take one card C1, one card C2, and it's just C1 get value compared to C2 get value. And that's it. This is actually transformed. It's syntactic sugar. So the Java compiler will transform this into the instantiation of the right comparator for you under the hood. We're now reaching the last part of this case study slash podcast, let's say, which is what should we do when we're offering multiple services? Because we've seen that I can be comparable, I can offer comparator, I can also be iterable, I can be clonable, I can be random access, like all those kind of things that we've seen together in the last 2 lectures. Well, how should I work with those ones to expose them? So it's easy when you only have one, because, well, then you expose this one. An array list, it's a list that's done, and you're good. But what should you do when you have more than one thing? So let's add something a little bit more complex to the case study we're working on, which would be inspecting the content of the card deck. So we want to inspect the content. We want to know what's inside. To do this, I need 2 services. One service is actually finding a way to iterate, like getting something that gives me access. And as long as I have something that gives me access, well, I can actually use it to iterate, okay? Think about this a little bit. I'm not talking into implementation details. I'm not talking about for loop, while loops, range, enumeration, whatever. This is not my problem. I'm talking about the functional behavior, the functional services, the functional features that are needed inside my code so that I can inspect whatever it could be, whatever collection it could be, okay? It's basically give me a way to iterate and then support the iteration. So this is quite classical. Java gives it as 2 services. The first service is iterable, not iteratable. And iterable, it's basically gives you an iterator. Okay, that's something that you will use to iterate. Not a for loop, not a while loop. We don't know, we don't care. It's just like, I need to inspect, I need to go through something, give me an iterator. And the iterator, it's basically gives me two functions. Has next, can I go to the next element? And if so, the next function that gives me the next element. With those three abstractions, give me an iterator. And on an iterator, I can call, can I go further? Has next, or is it, can you give me the next element, sorry, this is next, and then you can go through. So if we think in terms of responsibility, I can make my card pile, my deck, iterable, okay? I will have my card pile that realizes the iterable interface, and the iterable will give me the iterator. And when I call iterator, it's basically give me something that implement the has next and next elements, okay? And again, that's a delegation process. My card pile is built on top of a list. So I will basically, and the list can be iterated. So I will say, oh, when you want the card pile iterator, well, give me the one from the list. So I'm not creating it, I'm not implementing it, just like, oh, I'm delegating because someone else knows how to do that on my behalf. This is the list of cards. And this can be used actually, because each time you're using a for each loop in Java, which is this kind of situation, like I have a student S, which is part of a list of students, this is actually translated. It's again syntactic sugar. So the compiler will transform it for you into something which is exactly this. I'm taking an iterator over students, which is students.iterator, and the end condition is iterator does as next. And then I'm getting the student S as next, and I'm doing my job. Okay, so it's just like a nice way of writing this code. But those two codes are 100% equivalent, and you would not make any difference. You wouldn't see any difference in the bytecode by using the one on the top and the one on the left. Which brings us to this cool things, because it's important to understand how it works under the hood, but that's also important to get the benefits. Why is it working that way? Why it is the right way to design thing? Well, basically now, if my card pile offers iterable, I can iterate over my card pile using classical for loops, because it's given me for free, because I'm using the right abstraction, and Java was defined on top of those right abstraction. So anything that realizes the iterable interface can basically be iterated using this for loop, and it costs me nothing. It's just like totally free by design. And this is how I kind of like, I'm integrated as the inspection level. Okay, I'm not exposing any internal details such as the size of my card deck, getting the elements at index 1, 2, 5, 10. Not my problem, just getting how to go through. And by knowing how to go through, well, I can reuse all the stuff that are built on top of how to go through. But now, how can I like compose all those services? Because I can be shuffled, I can be iterated, I can be cloned, I can be like compared, like I have all these kind of things. So what should I do? Well, let's start simple. We only have 3 services, okay? I'm implementing 3 interfaces: shuffling, drawing, and being inspected. That's the 3 interfaces. And remember, we're really typing our programs according to public interfaces, not the concrete classes. So the point is not to go into the details, but find the right abstraction, because you've seen all the benefits of programming at the right level of abstraction in terms of software development for evolution and maintenance. So I have like 2 decisions that I can take, 2 extreme decisions. One decision would be one single interface that will compose all those 3 responsibilities. So being a card deck means that I can shuffle, I can draw, I can being inspected, and that's it. And it has all the methods in one single interface, which represents, which annotates, which gives me the cohesion of being a card deck. Or I can go the other way around, and I can say, no, I know how to shuffle, and I can shuffle stuff. A card deck being one of the stuff that can be shuffled. I know how to draw cards, but well, drawing, it's an abstraction of drawing stuff. So again, drawing card is just drawing stuff when stuff is a card. Being inspected, we've just seen it. It's all about iteration and iterability. So if I can be iterated on, then everything's fine. So do I need to put all those stuff together when I have those nicely separated and reusable interfaces? Well, let's compare. If I go for the dedicated interface, that clearly reifies the business logic. Okay, my business logic is being a card deck. All those methods are cohesive with the notion of being a card deck. Makes sense. But there's two red flags. First red flag is, will this interface be reused? I mean, if we're creating an abstraction, it's to give us like cohesion, give us readability in the source code, which is kind of cool, but also find a way to be lazy and reuse it in the future. We've seen that by reusing iterable, I'm able to use a for loop. By reusing comparable, I'm using to be sorted. I can be sorted quite easily. So if my interface, my type will be used only once, then that might not be a good candidate because I can use the class directly actually. And in terms of coupling, if I put all those methods into one single class, it means that my code will be coupled to all those methods. And maybe if I'm talking about sorting, I don't need the shuffling. If I'm talking about inspecting, I don't need the shuffling or the sorting because I'm just comparing or I'm just iterating. You see what I mean? So there's huge pros, which is business logic 100% cohesive with my problem. And there are the huge drawbacks, which is, well, no one else is going to use it and you're improving coupling. Not good. Second option, keeping everything separated. First, cons, it increases maintenance because instead of maintaining one single interface, one single type, I have to maintain 3 single types, okay? Which means 3 classes, 3 interfaces, which means 3 different files, need to document them, need to integrate, need to explain. That takes a lot of time. But I'm maximizing modularity because then I can pick the one I want to use. And I'm minimizing coupling because I'm using only what I need. If I have a card pile and I need to sort it, I can consider the card pile as just something that can provide comparison. If I need to shuffle, it's just something that provides the shuffling system, shuffling service. So that's basically this idea. I have the card pile, which is concretely something implementing on top of a list, and it has some concrete details. But from a usage point of view, one guy can decide to just iterate on top of the card pile to inspect the deck, and that works, and has no idea that it can also be shuffleable, that has a card source and kind of things. Not a problem. Just I want to iterate, let me iterate. This guy wants to shuffle the card deck before, for example, drawing the card. Very same. Very no need to know the details. Okay, this is shuffleable. I'm just going to use it. Card source, well, no one's using it yet, so don't care. But now, if I want to do both, well, I can link myself to the card pile, but that would be, we said that we prefer to type at the interface level than the concrete class. Because if I type with a card pile, I'm also getting shuffle. And I don't want shuffle because I want to be coupled. I want to use only those 2 services. So I can go for the card source and cast it to something iterable, but that would not be good because casts are kind of like evil in object-oriented programming because that's where we're kind of like slapping the type system and the object-oriented message dispatch in the face. So we don't really want to do that. So maybe there's a way to organize this in a better way than having those things completely separate. We said that everything at the same space, everything at the same interface doesn't work. Everything 100% separated. Nah, it has cons too, though. Not really good. Well, actually, classes in phase, they are first-class citizens, so you can organize them as you wish. So if you do this and you actually carry on the semantics of what you're doing, then it becomes way clearer. Like you have the notion of iteration. Okay, I can iterate over something, and it happens that what I'm iterating over is a card source. Meaning that when I'm using the card source, well, I also get the iteration for free because card source is an extension of iterability, of the notion of iterability, okay? And that's what we wanted on the last slide. We wanted the card source and the iteration at the same time because I'm kind of like drawing and iterating to check stuff out. And if I want to shuffle, then it becomes just shuffleable. And that's it. And so with this, all my different consumers are kind of like okay with the way they're using the service and they're using the system, which is kind of cool. So separating is one thing, and then assembling the different services you're providing in a way that makes sense is also something that is important in terms of software development. Because with this, remember in the previous lecture, all the different interfaces for collection, I can decide between a list, a set, a collection, or those kind of things. Well, you're basically recreating this. And by recreating this, all the flexibility, evolution, capacity for evolution and maintenance that you do have in classical object, well, you're providing it in your application. So you're giving like extension points where you can introduce new variation without having to change anything in your code, which is pretty cool. To conclude, the takeaway message is that there is no silver bullet. There is no golden solution that will work whatever the context. And that is your job as software engineer to find the right solution for the right context. Characterize the problem, identify the different solutions that you have in front of this problem, and select the best or the least worse. But in any case, select something for a good reason and be able to kind of like express this good reason. So we've seen together how to embed a comparison. So giving the responsibility to a class works well when there's only one way to compare, and then it gives us lots of benefits, and it really goes into the encapsulation information hiding pathway. That's pretty cool. But if we have several ways of comparing the cards, and we can't do that anymore, and we need to go into the externalizing approach, which is a comparator instead of using comparable, because this is like a variation point that we do need. And at all costs and by all means, external factors should not influence the content of your objects, okay? The object is kind of like a cell, independent, and it's a black box, and nothing from the outside should influence its internal decision. And now that we are separating everything and we're typing our things using the interface more than the concrete class, then we're like, okay, how can we organize those layers of abstraction and those way of designing software in an evolutive and maintainable way? And this will happen all the time. And there's, again, no silver bullet. So it's like, do it, realize where it's wrong, improve it, and try to converge to the right solution, the right here being the least worst. And then by using interfaces, hierarchized interfaces, you can find a way to maintain this flexibility while having this kind of nicely organized hierarchy. Defining such hierarchy is pretty hard. Then we'll have like other lectures related to model design and modularization and type hierarchies and stuff like this. So this is just the beginning. But that is the very point of what we're going to do. Remember, we are moving from software programming to software development. So we're kind of like considering that we know how to program, we know how to write code, and this is, of course, not over, but this is kind of like not what we're focusing on. And in this course, we're focusing on how to organize the code so that it's not just about programming, it's about development. So it becomes maintainable, capacity for evolution, testable, good for version control, and all those kind of things. Thank you very much for having attended this podcast / case study / lecture. I'll be back on Friday. So Friday we'll be back to regular lectures in MDCL building, and you'll have the opportunity to send me a message on Teams. So really use it. There might be stuff that you don't understand in the lecture, questions or stuff like this. Shoot a question in the lectures channel. There's no stupid question. If you need clarification, ask it. It will benefit for the class, and everything will be good. Thank you very much for having watched this video, and see you soon on Friday. Bye.